Problem number 8. We need to find the number of solutions to log 3x equals 4 times sine x. Okay, so first of all, there's no way we can really solve the equation. We just need to find the number of solutions. For such kind of problem, a typical strategy is to draw graph and to figure out the number of intersections geometrically. So let's first draw the graph. So the strategy. Draw two graphs. So first, let's draw the graph of 4 sine x. The largest value. So first, let's draw this. The largest value is 4. So we have so this is what we have. All right. So 4. The largest value is 4. All right. Now let's draw the graph of log 3x. X is always positive. When x is 1, this is 0. Okay, so when x is 1, so this is 1, because here this is pi. This is 2 pi, 3 pi, this is 4 pi, all right? Okay, so we draw the graph of log, we start from here, and then all the way, I use red, so all the way, we have that. Okay, now if we try to count the number of intersections, let's look at within each cycle. Let's look at the intersection, the number of intersections within each period. So here what we have, so this is the first period, this is the second period, and this is the third period. Here, this is 6 pi, right? Okay, so within the first period, we just have one intersection. This is 1, this is 2, right? So 1 and 2, and this is also 2. And this is also 2. So the point is like within each cycle, each period, except the first one, for the other is like 2, 2, 2, 2, 2. So we just need to figure out what is the last period the graph is going to have intersection. So let's look at the last period when they have intersections. Okay, because here the largest value is 4, right? And we have the log 3, this 81 is 4. So we just need to figure out, we need to compare 81 with pi. So we have 81, clearly, we have 81. This is less than 26 pi, that's bigger than 25 pi. So the last cycle is here. If I draw the graph, right, we have, let's just put here. So this is 22 pi. This is 23 pi. This is 24 pi. Here it's 25 pi, and this 26 pi, right? Okay. We have $81 is here. So this is 81. 81. And that's the place the logarithm function attains value 4. This is 4. That's what we have. That's what we have. Okay, so if we go back to the number of intersections, again, this is what we have here. This is 2, and this is 2. So how many cycles do we have? We have 13 cycles, right? But the first one, because the first one has only 1, so we have to minus 1. From here, we conclude. So conclusion. Maybe I put it here. 13 periods. Each period has each one has 2 intersections, except 2 intersections. Except the first one. Except the first one. The first one has only 1 intersection, so that's 1. So I get the total number. So get the total equals 13 times 2 minus 1. That's 25. Problem number 9. Here we have a triangle ABC. We know the largest angle, here we set to be A, is twice of the smallest angle. So angle A is twice of angle C. And then we also know 3 sides lengths are 3 consecutive integers. And what we need to figure out is the parameter of the triangle. All right, so we can set 3 side lengths. This is the longest one, so that's n plus 2. This is the smallest one, is n. And this is the middle one, that's n plus 1. Because we know they are consecutive, the question is what's next? For this kind of easy problem, what I mean is if we know one angle twice or the triple of another angle, one way you can try, that's kind of common, is try to bisect or trisect that angle. So for here, let's say we bisect the angle A, right? So let's say this is alpha. We put this one as alpha. Therefore, this is alpha, and this is 2 alpha. We bisect it. So bisect angle A. All right. So when we see bisect an angle, one thing that we should immediately think of is the angle bisect theorem, right? So number 1. So it's okay. So by angle bisect theorem, we have AB over AC equals BD over DC. So AB over AC, this one is n over n plus 1. Therefore, I can introduce, say, lambda. I can say this part is n times lambda, and this part is n plus 1 times lambda. I put the lambda just represents the ratio, because the ratio is the same, right? The ratio is the same. Okay. All right. Then we have, from here, we just deduce the n plus 2 equals n lambda plus n plus 1 times lambda. So we have the lambda is n plus 2 over 2n plus 1, right? We derive a relation between the parameter lambda I introduced with the integer n that we need to determine. Of course, this is not enough, right? Because we have 2 variables, we have only 1 equation. The question is, what's next then? As we have mentioned multiple times, if you have a geometry problem, especially if the geometry problem in AMC8, usually it's kind of straightforward. But in AMC10 or AMI, you just need to make more efforts. A common strategy you can try, let's say you have used all those obvious things, and you find it still hasn't been solved. Then you can try to find hidden similar or congruent triangles. Keep this in mind. Find hidden, similar, or congruent triangles. This is a very powerful tool when we handle a geometry problem. Usually for more complicated things, you probably need to add helping lines to construct useful similar or congruent triangles. All right, so let's see here. Do we have similar or congruent triangles? The answer is yes, because if you look at these 2 angles, the B is common angle, right? So here you have 2 alpha, and this is also 2 alpha, right? It's also 2 alpha. So from here I deduce, so number 2, I have the triangle ABD is similar to triangle ABC, right? Because they have 3 equal angles. So we apply the ratio. So I apply the ratio. I have the AB, this is from triangle ABD, over the corresponding, because this is the longest one, over the BC, shall be the same as BD to the alpha over AB, okay? Now, if I put all those data into this ratio equality, I have the n over m plus 2 equals, this is n lambda over n, right? Okay, so we cancel n, and we get the second equation. That's lambda equals n over m2. So our two equations, we can combine them together, 1 and 2, right? From here, we get, so from here we get this n plus 2 over 2n plus 1 equals n over n plus 2. So that here, so here we have the equation of n. So what we do is, all right, so our two fractions, so we use the cross multiplication, and this gives us n times 2 squared equals n times 2n plus 1, right? Okay, all right, let's simplify this. This is n squared plus 4n plus 4. Let's look at the right-hand side, equals 2m squared plus n, right? Okay, we cancel 1m squared, and we cancel 1n, this becomes 3. So I have, it's m squared minus 3n minus 4 equals 0. And from here, we can just factorize this. It's m minus 4 times m plus 1 equals 0. So I get n is 4. One side is 4. So 3 sides is this is 4, this is 5, and this is 6. So if you have 4, 5, 6, one angle is twice, the largest one is twice of the smallest one. So the parameter is 4, 5, 5, 6. That's 15. So here we use two things. Number one, the most crucial part is we draw a line to bisect the A. As I said, that's kind of a common trick when you handle the situation if one angle is twice of the other. All right, and then we use angle bisect theorem to set up some ratio between BD and CD. That's not enough. The next step is we find the two similar triangles and derive another ratio. We combine the two together, we are able to decide the length. Okay, problem number 10. Here we want to expand x to the power 7 plus x to the power 5 plus 1 to the power 20. The question is, we need to find the coefficients in front of x to the 17 and x to the power 18. All right, so let's look at this. We have x to the 7 plus x to the power plus 1, x to the 7 plus x to the power plus 1, and we multiply 20 copies together. Okay, now our goal is to look at, so first let's look at x to the 17, right? We need to find out the coefficient in front of x to the power 17. How can we come up with x to the 17? Well, what we need to do is we need to use x to the power 7 and x to the power 5, given the combinations, to get this x to the 17, right? Okay, clearly there's only one way to do that. What we can do is x to the power 7 times x to the power 5 times x to the power 5. That's only one way we can do. In general, so what is the general format? General format is, okay, so we have, we're basically looking for how many k of, k represents how many x to the power 7 we use, and n is how many x to the power 5 we use. Then we, of course, we have x plus n should be less or equal to 20. It cannot go beyond 20, right? Because we need to use the total power is 20. And then, of course, we have 7k plus 5n. That's the combination of powers we have. This equals 17. There's only one solution. So that's k equals 1 and n equals 2. Okay, so we need, so that means we need to choose the 2 of x to the 5. That's 20, choose 2, right? Because we have, in total, we have 20. We need to choose from this 20 copies, we choose 2 copies. From that 2 copy, we use x to the power 5. And then we choose the remaining 18, we choose 1 for the x2. So this one is for the x5, and this is for the 7, right? For the 7. Okay, let's calculate this. This one equals 18 times 190, and this one is 3,420. Similarly, let's look at the next power, that's x to the 18. So, okay, now we want x to the 18. What is the coefficient? Well, if we go back to this format, that just means we need to find a combination. 7k plus 5n equals 18. And it's clear to see there's no way that you can find k and n such that this works. So this is impossible. And that implies there's no x to the power 18 term, which just means a18 equals 0, right? This one equals a17. All right. Accordingly, our n is a17 plus a18, which is 3420. If we just care about the sum of digits, the sum of digits is 9. All right. So here the point is, when we try to expand the product of polynomial, right? So then we look at the combination. How can we, let's say we focus on the coefficient of a single power. So here is x to the 17 and x to the 18, right? So we just need to find the suitable combinations, which will give us x to the power 17. So here, there's only one way we can do that. That's x to the 7 times 2 copies of x to the 5. That means if we expand that one out, we need to choose which two we are going to use, the x to the 5, and which one we are going to use for the x to the 7. The remaining we just take to be 1. So that's just a combination problem, right? 20 choose 2, and then 18 choose 1. Okay. Problem number 11. A robot flips a coin, a fair coin, repeatedly. There are 2 players. One is Daisy and the other one is Patrick. Each of them picks a special sequence. Daisy picks the sequence is head, tail, tail, and Patrick picks the sequence tail, tail, head. The rule says whoever the sequence appears first is the winner. When you first look at this, you might think, oh, edge, head, edge, tail, tail, and tail, tail, head, they're kind of similar, right? If you just focus on these 3 outcomes, for each of them, the chance is 1/8. That's 1/2 times 1/2 times 1/2. So you might think it's equal likely, you get a 1/2. In fact, that's not the case. What we have is this one is more likely to happen. This is more likely to happen. Likely to happen. Now, why is that? That's because in order, so let's look at Patrick. So in order for Patrick to win, so here's the claim. In order for Patrick to win, the first one has to be head. So it has to be head, 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 all the way to, no, sorry, it has to be tail. Tail, 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 all the way to tail, tail, head. So let me write it down. So here's the claim. The claim. In order for Patrick to win, we must have things like this. Have tail, tail, head, right? And then tail, 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 head. And or tail, 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 head, or tail, 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 head. Okay. So my point is this. So that's exactly what I said. It has to start with tail and all the way, tail, 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 all the way to the pattern tail, 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 head. Okay. On the other hand, if we focus on the Daisy, then of course it's not that case. We can have either, we can start from head or tail, and they can somehow kind of repeat, alternate. For example, we can have head, head, tail, tail. That's for Daisy to win. Or we can have tail, head, tail, tail, right? So this is also in this kind of scenario that Daisy can also win. So the point is kind of clear that Daisy has more situations that she could win. All right, and meanwhile, we find it's easy to compute the probability that Patrick wins because it's the pattern is kind of simple. So let's calculate the probability. So let's calculate the probability that Patrick wins. All right, so we have this one is 1/8. This one is 1/8 times 1/2, right? So this is 1/2. And then here is 1/8 times 1/2 times 1/2, right? And this is 1/8 times 1/2 times 1/2 times 1/2, right? So this is 1/2, this is 1/2, 1/2, 1/2, 1/2. Okay, such and such. So if we add them together, therefore the total probability, the total is 1/8 plus 1/8, and we can pull out, this is 1/2 plus 1/4 plus 1/8, and all the way to 0, right? Okay, now we know this one is geometric series, and if you add them up, let me put it here. So if I 1/2 plus 1/4 plus 1/8 plus 1/16, this one added together equals 1. Okay. All right, so then if we put here, this equals 1/8 plus 1/8 times 1, and this is 1/4. So the probability that Patrick wins is 1/4. Therefore, I claim, so the probability that Daisy wins is 1 minus 1/4 is 3/4, 3/4. Now, some of you might wonder, wait a second, how do you know it's 1 minus 1/4? Is it possible that none of them wins? Well, of course it's possible. Let's say if miraculously it gets head, or tail, all the way to tail or all the way to head, then none of them wins. But the point is, the probability, here we are talking about probability, the probability that none of them wins is 0. So let me put it here. So here's what I want to demonstrate, the probability that none of them wins is 0. Well, let's see. Okay, so let's see. What is the scenario that none of them wins? That could happen if and only if for these two patterns, like this pattern. So this means patterns like either this one, head, tail, or tail, head does not appear, right? Okay, let's just focus on one. It's enough to demonstrate the probability is 0. Now, this one does not appear. Let's say if this one does not appear, if, like here, so if tail, head does not appear, let's look at what we have. Because the robot flips the coin infinitely many times, we have, let's see, that's we have, flip infinitely many times. Okay. Now I can regroup these flip coins into 3, 3, 3, 3. So 3, 3, 3, right? Okay, so if this one does not happen, then the probability for each 3 is 7/8, right? Because the probability for this one is 1/8. So this, what we have is 7/8. This is also 7/8. This is also 7/8. All right, then what we get is the probability is at the most. So we get the probability that TTH does not appear is at most. It's not exactly, but it's at most. It's 7/8. 7/8 times 7/8 times 7/8, all the way to 7/8. Now, when you fix the number and you multiply them together, we know this is going to be 0, right? It's going to be 0. All right. So the conclusion is we get what I put it here. The probability that none of them wins is 0. Therefore, if I know, so in the sense of probability, with the probability of one of them is going to win, right? If this wins, then the other one loses. So if I figured out, after I figured out the chance that Patrick wins is 1/4, then the chance that Daisy's wins is 3/4, right? 3/4. All right. Okay, so finally, I want to mention this problem is a special case of something called Penny's game. So this is a special example. A special example of the so-called Penny's game. All right. Problem number 12. This is a trigonometric equation. Here says sine 4 pi x plus cosine 7 pi x equals 0. To solve a trigonometric function, equation, what I like to do is to switch all involved trigonometric functions into the same kind. Like here, we have a sine and a cosine. So I'll try to switch both of them to either sine or cosine. Either is okay, depends on which one you feel more comfortable to handle. So I will go with a sine function. Okay. So step 1, I'm going to derive, step 1, I'm going to derive a general expression of solutions to this equation, because this equation itself has infinite many solutions. So I'm going to find a general expression, derive a general expression of the solution x. All right, so let me copy down the equation here. Sine 4 pi x plus cosine 7 pi x equals 0. Okay, now I move sine x to the other side. So I have cosine 7 pi x equals sine 4 pi negative sine 4 pi x. All right, then we can absorb the negative sign into the inside, because sine function is odd function. Odd function means sine negative a equals negative sine a. All right, so this one equals sine negative 4 pi x. Now I'm going to switch cosine to sine. Well, the way we choose cosine to sine, we use pi over 2, because I know sine a equals cosine pi over 2 minus a, right? So this one equals sine pi over 2 minus 7 pi x. Okay, so here I get equality that involves two sine functions, right? Sine pi over 2 minus 4 pi x equals sine negative 4 pi x. Now let's recall, if I have two angles with the same sine value, what can I say about the relation between these two angles? So if sine A, let's recall, if sine A equals sine B, then we have two situations. Situation 1, A equals B plus 2k pi. Right? 2 pi is the universal period for all trigonometric functions. Or I have A plus B equals an odd multiple of pi. So in particular, if A plus B is pi, then they have the same sign value, right? Okay, so we have two cases. One is A equals the B plus 2k pi. So here pi is any integer. So this notation just means any integer. Z is the universal notation for the set of integers. Or we have A equals 2k plus 1 pi minus B. So k is also any integer you like. Now, if we apply this to the equation here, we deduce, we have two cases. So here we imply case one. So case one, we have 2k pi plus pi over 2 minus 7 pi x equals negative 4 pi x. Okay. So from here, then we can solve 3 pi x equals, what do we have? It's 2k pi plus pi over 2. So if I simplify, if I divide 3 pi on both sides and I simplify the expression, this will give me 6, 4k, this is 4k and plus 1. And it's because I require x to be positive, so all the possible choice of k is k0, 1, 2, and goes up. So in particular, I can write this just as 1 over 6, because I need this one to be positive. So 1 over 6, each time it goes up by 4. So 5 over 6, 9 over 6, 13 over 6, and such, right? So here I choose not to simplify those fractions in order to keep a uniform form. So this is case 1. Now let's look at case 2. Case 2. Case 2, I should have is 2k plus 1 pi minus pi over 2 minus 7 pi x equals negative 4 pi x, right? Okay, so from here, I can derive 11 pi x equals 2k pi plus pi over 2. Now again, I just divide 11 pi on both sides and simplify the expression. I will get x is 22. Yes, 4k and plus 1, but you have a minus. You have, sorry, you have minus sign. Minus, okay. Oh, minus. All right. Now, because I need the x to be positive, so for this case, I should choose k to be negative. I start from -1, -2, and da, 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 da. Again, if I write this as, say this is as an explicit expression. So the first one will be 3 over 22, and each time it goes up, the numerator goes up by 4. The second one will be 7 over 22, and then I have 11 over 22, 15 over 22, and such, right? Goes up. Okay, so let me label. This is the category 2, and this is the category 1. Now I need to figure out, so if I combine these two collections together, I just get the whole collection of solutions. Now what we need to do is we need to figure out what is the 100th number in the sequence, right? Okay. To simplify the process, let's make an observation, simple observation. Let me put it here. So I'm going to have the following simple observation. So observation. If I have sine 4 pi x plus cosine 7 pi x equals 0, then x plus 2 is also a solution, right? That's just because sine and cosine, they both have a period of 2 pi. So this tells us we just need to look at, so by this we have right. So we just need to look at the number of solutions within the interval 0 and 2, right? And then, okay, we figure out the number of solutions within interval 0 and 2. Each time goes 0 to 2, it's the same. The pattern from 0 to 2 is the same as from 0 to 4, from 2 to 4, and from 4 to 6. And then we just divide by look at the remainder when 100 divided by the number of solutions with 0, 2. Okay, so let's draw it. I have, so this is the, let me summarize, let me put it here. Let's, so I have two categories of solutions. So 2, so now here is step 2. I need to figure out the 100th solution, right? Positive solution. Okay, all right. Now let me draw. Okay, so before let's recall, I have these two classes of solutions. So 1 over 6, 5 over 6, 9 over 6, 13 over 6. So this one already goes beyond 2, so we don't really consider it. But let's put it here. And the second class of solution, which is start from 2 over 22, 7 over 22, 11 over 22, 15 over 22. Okay, so what is the one that is before 2? That is 22, because the remainder has to be 3 when divided by 4. Okay, so this one should be 43, right? 43, and of course goes on and on, but we just need to stop right here. So this. Okay, now let's mark those solutions on the interval from 0 to 2. So middle, this is 1, this is 1/2. Okay, so this is 3 over 2, this is 1 over 4, 3 over 4, right? Okay, so this is 5 over 4, right? So this is 7 over 4. Okay, the first category, we have only 3 of them that's within 0 and 2, so that's right here. So this is right here. So the first one, 1 over 6, and then we have 5 over 6, right? So this is the 5 over 6, and then we have this 9 over 6, that's right here. So this is 9 over 6. Okay, so we have 3 from the category 1, and then we look at from category 2. So that's the first one is right here. So that's 3 over 22. Right, so we have 3 over 22, and the next one is 7 over 22. Okay, so we have the 7 over 22. If we do the calculation, you will see 1 over 6 is less than 7 over 22, right? Which is clear. Okay, all right. In fact, 722 is not here. 722 is it's larger. It's not very accurate, but it should be large. It should be large than that. Cover this. All right. Okay. So then we have the next one is right here. So 11 over 22 and such and such. Okay. And the last one is right here. So that's 43 over 22. Now let's see how many do we have. Here we have 3 of them. So 1, 2, 3. So that's 3 from here. And how many we have from here? We have 11 from here, right? Okay, so we have 11 from here. Okay. Now, then we have in total, we get the number of solutions within here is 14. So there are 14 solutions. So we get the number of solutions within the interval. This is 14. Okay, so then we look at the remainder 100. We look at 100 divided by 14. So that's 796. We get the remainder is 2. So if I draw the picture, we start from 0 to 2, 0 to 4, and all the way. Here is 13 to 14, right? We have 7 of them, so it's 1 times 2, and this 7 times 2. Okay, also we have 2 remaining parts, right? So the remaining part is 2. Okay, so if we go back to the picture here, if I just look at what happens within the interval 0 to 2, I figure out it's easy to see. This is the number 1. This is the number 2, right? So if I put the picture back to here, I will get this and the second one. So the first one is 14. It's 14 plus 3 over 22, and the second one is 14 plus 1 over 6, right? So that's so this is what we are looking for, because the remainder is 2. So it's 14, 1 over. Number 13. Here says we have a bigger cube it consists of a lot of small cubes. Then we draw a line pass through the big cube. The question is, what is the largest number of small cubes the line is going to pass through? The main difficulty about this problem is number one, it's 3-dimensional, and number two, the cube is large. There are quite a few small cubes. So it's not easy to visualize if we just look at this specific case. So our strategy is, let's first look at some simplified situations. And from there, we are going to derive a general formula to see what happens. Here, when I say a simpler situation, means let's look at what happens in 2D, and then we extend from 2D to 3D. This is also a general philosophy in math, not only in math computation, but also it's a very important method in doing math research. If you have a complex situation, you first consider a simpler situation first, and then try to derive those most essential points in the solution, and then extend it, generalize to the more difficult scenarios. All right, so let's see what happens in 2D. Okay. Here I have, this is 2 times 2 and 3 times 3, right? Well, these two situations are simple. I can just draw the two lines that will give us the largest number of small squares that they will pass through. So the first one, clearly I can do it. There are multiple ways to draw, but let's say for this, I can just do this, right? All right. And for the next one, we can do right? So that's what we can do. Okay, now the point is, let's see whether we are able to derive some general mechanism behind how should we design the line. For that, I'm going to define something called interior lines. Interior lines means those lines, either it's horizontal or vertical, they are inside of the square. Here I have, this is the interior horizontal line, and this is interior vertical line. Okay, so we have two ones. One is horizontal, and or you have vertical. All right, so those are horizontal, vertical. So for here, for this one, I have this is interior horizontal line. This is interior horizontal line. This is a vertical horizontal line, and this is a vertical horizontal line. Now, let's look at this case. The first square it pass through, we can just say is the special one. And then after this, you see every time when the line pass through an interior line, it is going to add one more square to it, right? Okay, so we have this time we add 1, right? And then add the next one. So we have from here is okay. So basically the largest number, the number of, we say the largest number of squares it passes through equals the first one, the special one, and just plus the number of interior lines. This is kind of clear. If we are able to do that, you see, because in order to pass a square pass a small square, except the starting one, you have to pass through an interior line first, right? In order to add one more. Okay, so we get this is from here we get this is just equals star plus this is 2 times 1, right? 2 times 1. So here we have 3. This one is similar. You start from the special one, which is the starting point, and then every time when the line intersects, pass through interior line, it will add one more, right? So add one more here. So we add one more. So this is we add one more, and then add one more, and then add one more, and add one more. Add 4. Exactly the number of interior lines, right? Okay. So we get again. This is equals the first special one plus, right? Plus the number of interior lines. And for this case, is the first one plus 2 times 2, which is 5. That's 5. Okay, so we have to extend this. It's kind of clear. In general, if you have m times n square, you draw a line in order to get the largest number of squares. What you should do is, of course, you should try to pass through all those interior lines. That's the best you can do, right? It's kind of clear. So we derive that conclusion. Oops. For n times n squared, right? The largest number of squares, the largest number of small squares it compares is the first one. So this is the special one. So first one plus the number of interior lines, right? Interior lines. Okay. So what is that? That's 2 times n minus 1, right? So that's the number of interior lines. Okay. So we just get is 1 plus 2 times n minus 1, or you can just write it 2n minus 1. So that's the formula for the square. Now, the next step is, can we extend this from 2D to 3D? Now, for 2D, as we just mentioned, just explained, we just look at those interior lines, horizontal or vertical. Then naturally, if you go to 3D, what you should look at is those interior planes, right? It's horizontal, a vertical, you have 2 direction verticals, right? In order, think of this, the mechanism is exactly the same, except that in 2D, it's easier to visualize. In 3D, it's the same. We start from the first one, and then each time when we pass through a plane, either it's like this direction, or it's like this direction, or it's like this direction. So each time when pass the plane, you are going to add one more. Right, so that's the best you can do. You just design, you just go a line, the line, if you go like that, you get the largest number of squares. So the formula is the same, the 1 plus the number of interior planes. So from here, we extend, so my point is now, if we extend this to high dimension, say, we're going to extend to 3 dimension. We have for n times n times n cube, the largest number of small cubes the line can path is special one. So again, it's a special one, which is 1 plus the number of interior planes. Which is equals 1 plus 3 times n minus 1. So that's 3n minus 2. So this is what we derived if we look at what happens in 2D and then we extend to 3D, and which is very reasonable, as we already explained. Now, we can look at the special example, say if I have the cube, if I have a 2 times 2 times 2 cube, all right? Okay, so let's mark those interior planes. So this is interior plane direction. And then we have, this is also interior plane, right? And we have one more interior plane. This one is also interior plane. Okay, so if we start from here, from this, so this is our starting point as we did for the 2D starting point. Starting from this small cube, each it's going to pass through all those small. Okay, so here we have 1, 2, and 3 interior planes, right? We are going to pass through all those interior planes. Okay, now you see when each time, as we said, each time when it passes through an interior plane, it's going to add one more. So here we add one more cube, then add one more cube here, and then add one more cube here. So you see the number of cubes is the special one plus 3 times. So here is we have 3, right? So it's 3 times 1, right? So for this case, it will be just 1 plus 3. So this is the 2 times 2 times 2. 3 is 4. So for our specific case, for our case, n equals 2020. So the number, therefore the number is, we apply the formula, 3 times 2020 and minus 2. So that's 6060 minus 2 is 6058. This is the largest number. So as we have seen, the point is you focus on those interior planes, right? Start from the first one. Each time when you pass through an interior plane, it's going to add one more, add one more, add one more. So therefore, the best you can do is try to pass through every interior plane. So you add, so therefore, the total number of cubes you can pass is the first one plus the number of interior planes. Problem number 14. Here we have a circle that is inscribed inside a regular hexagon. We need to find the area of this red triangle. What we know is the side length of the regular hexagon, that is 2. Then by the, we know this angle is 30. We can quickly, this angle is 30 degrees. This is 90 if you connect because tangent, right? So, and we utilize the special ratios within the right triangle, 30, 60, 90. So that's 1, 2, 1 square root 3 and 2. If this is 1, then we quickly get this one is the square root 3, right? So the diameter is the square root 3, 2 times square root 3. Okay, now let's go back to what we want to figure out. We want to figure out the area of this right triangle, right? All right. So what I will do is I will connect the P with the middle point of AB. Let's say this one I denote as the H and the intersection as the G. All right. This PH is the diameter of the circle. So that is the, this part is 2 times the square root 3, all right? And also we know the triangle PQG, this one is similar. So obviously we have the triangle PQG is similar to triangle PAH, right? Now AH is 1, AH, this one is 1. So I have the area, of the triangle PAH. This is just the square root of 3. Now, in order to find the area, so this is what we need to find, the area of this. If you multiply the area of PQG, we just get the area of the triangle PQR, right? Now, in order to find the area, we need to find the ratio. To find the ratio. Find the ratio, we need to find what is the PQ, the length of PQ. Okay, so how we find the length of PQ? So this is what we need to do. We need to find the length of PQ. Let's use, let's add one more helping line. Let me do this. So if I connect the Q and H, because the PH is the diameter. So diameter is corresponding to the right triangle. So I get this one is a right triangle. Okay. Now let me single out what I have here. So this is the bigger right triangle. That is the P, A, and H. Okay, here we have 2 square root 3, and this is 1. Okay, now Q is Q is the height, right? Because the angle is 90 degrees. So this basically becomes the foot of the altitude. So this is the Q. What I want to figure out is the PQ. That's the line I need to figure out. Well, there are multiple ways to figure out the PQ, right? Either you can figure out the height first and use Pythagorean theorem, or I like to do is we are going to use some well-known equalities within a right triangle. So let's recall some facts. So this is something I like to use. So recall, if I have a right triangle, let's say this is A, this is B, this is C. Okay, this is just general one. So C is A, this is B. If I have this is perpendicular, this part I would say is X, this part is Y. Now by similarity, we have the following equalities. We have the A squared equals X times C, B squared equals Y times C, and you also have, which is not really needed, but I can put it here. So I have H squared is X times Y. Let me use the column. All right. Okay. Now I'm just going to use this one. So this is what we have. I have, by Pythagorean theorem, this part is the square root of 13, right? But then I have the question mark times the square root of 13. This equals 2 times the square root of 3 squared, that's 12. So from here, I get a question mark. The question mark equals 12 over the square root of 13. So this is the 12 over the square root of 13. All right, so then I get a ratio, right? I get the PQ over the PA equals 12 over the square root of 13 over the square root of 13. So that's 12 over 13. So that's the ratio between these two triangles. Now, if I translate to the areas, so area ratio, we should take the square of the ratio between their sides. So area ratio. I have the area of triangle PQG over the triangle PQG over the area of PAH. This is the 12 over 13 squared. So that's 144 over 169. All right, now we already know the area of this PAH. This one is just the square root of 3. We might just calculate this, it's square root of 3. So if we combine those things together, we get, from here I derive, right? So we derive the area of PQG is 144 over 169 times the square root of 3. Okay, so the red one is 2 copies of 8, and this implies the red one, the area of PQR. So we are, what do we want to calculate is the PQR, right? So the PQR, so the area of PQR will be just twice, 2 times that, twice of 8, so which is 288 over 169 times the square root of 3. All right, these two numbers, because this is what we want, n of n, right? Okay, so this is our n, this is our n. So we add them together, n plus n, 288 plus 169, so that's 457. 457. Okay. All right, so here are the main point. What is the main point? The main point is we need to add this helping line, HQ, and because the PH is the diameter, therefore this is the right angle. After we realize this one is right angle, what is left? You can either use, as I said, use those nice relations between line segments within a right triangle, or you can just use a Pythagorean theorem, whatever, to figure out the length of PQ, and because then use the similarity to figure out the area of PQG, then you multiply by 2, that's to give you the PQ.